Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to your YouTube channel Chandan Physics. In this video, we are going to discuss laws of refraction on the basis of Huygens theory. Let's begin. There are two laws of refraction. One is the sine of angle of incidence, the ratio of sine of angle of incident to that of sine of angle of refraction is a constant, which is known as the refractive index. That law also named as the Snell's law. Another one, the incident ray, the refracted ray and the normal to that of plane of refraction, or we can say the normal to that of plane that separating the two media are lie in a same plane. Let me prove these two laws of refraction on the basis of Huygens theory. Let x y the refracting surface, that is the refracting surface which separates here air as medium, here is a denser medium, air having refractive index 1, let the denser medium having the refractive index mu. In comparison to these two, air medium is rarer as comparison to that medium having the refractive index mu, and the velocity of light through that of air medium is c, velocity of light, let v be the velocity of light through that of denser medium. Let AB is an incident wavefront normal n dash AB the incident wavefront, incident plane wavefront which just incident on that of refracting surface xy. The normal take AL and MB are the normals to that incident wavefront AB. These are the incident rays. Let A n dash be the normal to that of refracting surface. Then the angle between L A n is the angle of incident I, that angle also I. Here the velocity of light in air is c and the velocity of light throughout that of denser medium let v. According to Huygens principle, each point on that of incident wavefront AB becomes a source of secondary wavelets. By the time the disturbance B reaches the point B dash, and A reaches the point A dash. That will be the normal. MDS. So, the time taken to reach the point B to B dash is same as the time taken to reach the point A to A dash. Therefore, the time taken from A to A dash, that is the distance to its velocity, distance A dash divided by velocity through that of medium V is equal to, again time taken to that of point B to B dash, B distance to that of velocity C. This two time are equal. Therefore, A dash is equal to V by C into B dash. How we found out the refracted wavefront? Let me draw the sphere having the center at A, radius as A dash. We draw that of sphere, and at that of case A dash B dash be the tangent to that sphere, which is nothing, that is the refracted wavefront. To find, here I write the time taken be same for both the cases as A to A dash and B to B dash. That from Huygens theory we know. To find refracted wavefront, what we have to do? Draw a sphere with center A and radius A dash, which is equal to V by C into B dash, the value of A dash. Now, draw a tangent. The tangent is B dash A dash from the point B dash. Then B dash A dash represents the secondary wavefront. Here the normals A dash L dash, B dash M dash to that of refracted wavefront represent the refracted rays. These are the incident rays, these are the refracted rays. AB the incident wavefront, A dash B dash is the refracted wavefront. Let we prefer an arbitrary point Q as we prove in case of reflection, that Q after refraction reaches the point Q dash through the point K. That will be the refracted wavefront. Therefore, the time taken to reach the point Q to Q dash here we consider a point, consider an arbitrary point Q on incident wavefront AB. So, after time t it reaches at Q dash on the refracted wavefront A dash B dash. Therefore, t is equal to the time taken to reach the point Q to Q dash, that distance, again this distance. So, time taken to travel Q to K is Qk, distance to the velocity of that of medium, here velocity is c, plus K to Q dash, here the velocity is v. Now, we have to evaluate what will be the distance Qk and Kq dash. To evaluating that one, we taken two triangles. Look at that figure. Here the angle of refraction also R, that angle also R, angle of refraction. From right angled triangle AQK, that is the right angle, taking sine of this angle AQK, sin I is equal to QK divided by AK, QK divided by AK. We have to get QK. So, QK is equal to AK sin I. Next, to find the value K Q dash, we prefer from right angled triangle Q dash B dash K, Q dash B dash K. Here sine of R is equal to K Q dash divided by K B dash, or k q dash is equal to k b dash into sin r. The values of qk and kk dash are put here. Therefore, we have t is equal to ak sin I divided by c plus k b dash sin r divided by v, or t is equal to ak sin I divided by c plus, in place of k b dash is written as a b dash minus ak, a b dash minus ak sin r divided by v, or t is equal to ak sin I plus a b dash sin r minus ak sin r, see here v, or t is equal to, taking ak as common to these two terms, we have a b dash sin r divided by v plus ak as common, we have sin I by c minus sin r divided by v. Let equation number 1. Here is the equation number 1, that is the equation number 2. Again same thing happened here. Since for the rays of different points on that of incident wavefront, the values of ak are different. That is why all the points on incident wavefront AB reach to that of refracted wavefront A dash B dash require the same time. Therefore, the time should be independent of AK. Since for rays from different points on incident wavefront, the values of AK are different. If the rays from all the points on incident wavefront AB went to reach the refracted wavefront, A dash B dash simultaneously, then t, that is the time taken, should be independent of AK. Therefore, equation 2 is independent of AK. that is AK sin I divided by C minus sin R divided by V is equal to 0, that term. Since AK does not equal to 0, therefore sin I by C minus sin R by V is equal to 0, as AK does not equal to 0, as it is independent of time. Therefore sin I by C is equal to sin R by V, or sin I by sin R is equal to C by V, C by V, which is known as mu, that is a constant is known as refractive index of denser medium with respect to air. The velocity of light in air C, velocity of light in that medium, sin I by sin R is equal to mu. We have sin I by sin R is equal to mu. Which proves the second law of refraction, and also is known as the Snell's law. Sin of angle of incident, the ratio of sin of angle of incident to the sin of angle of refraction is a constant. In this way, we prove the second law of refraction by using Huygens theory. We have to prove the first law of refraction. Look here, the incident wavefront AB, the refracted wavefront A dash B dash, and the refracting surface XY all are perpendicular to that of paper, to the plane of that paper, AB, A dash B dash and XY, as the incident wavefront AB, refracted wavefront A dash B dash and refracting surface XY are perpendicular to the plane of the paper, So the incident ray, that is LA MB, incident ray that associated with that of incident wavefront, and the refracted rays B dash M dash and A dash L dash, that is associated with that of refracted wavefront, and normal like that of N A N dash to that of refracting surface, which is associated with that of XY, all lie in that of same plane. Therefore the incident rays in that of case LA MB refracted rays here A dash L dash and B dash M dash and normal n dash are lie in a same plane, which proves the first law of refraction, which proves the first law of refraction, which proves the second law of refraction, which implies in this way the laws of refraction is proved on the basis of Huygens theory. So, with the help of this video lecture, you understand the laws of refraction on the basis of Huygens theory. We prove it. That will be the second law of refraction, that will be the first law of refraction. So, the laws of refraction is proved on the basis of Huygens theory. So, with this useful and informative notes, let me wind up this session. Thank you.